So I want to do a quick geometry review. I mean, not review of geometry theorems or whatever, but there's one particular aspect of geometry that I'd like to review. So the particular aspect of geometry I want to review is, you guys talk about René Descartes in geometry, right? Cartesian coordinates, it's a geometry topic, right? Okay, good. So in geometry, you are introduced to XY coordinate system, right? So you have x-axis and y-axis. Good. And maybe in geometry, you don't do this as much. I forget in which math subject this would have come up. But at some point, you should have learned something about rotating your axis. Like a transformation you can do where, this is the regular axis we are used to seeing. But if you have a point, if you have some point in this space that you would have represented with some coordinates x1 and y1. So if this point could have been represented as x1, y1, you should have been told how to kind of transform this so that you express this coordinates of this point for a different axis. I guess you could move this axis over, that's one, translate it, or you could rotate it. Good? At least you have seen rotated axis. I know you must have seen it because we do that in Physics 4a. But what we usually don't do, especially in Physics 4a, is go over more, I guess, abstract mathematical aspect of this. But you've seen rotated axis, right? And if I tell you this same point can be represented with this rotated coordinate axis, then what I draw hopefully will make sense. Given this point, I drop down a line that's perpendicular here. So this is my x1 prime. And something like this, call this y1 prime. And the same set of coordinates, it could be represented, or same point can be represented by one coordinate system or another coordinate system, x1 prime and y1 prime. Right? As long as you know how these two coordinates are related to each other, then it's a fairly simple matter of showing this equivalence. So what parameter would you need to kind of relate these two coordinate axes? You need to know the angle between the axes. The common way to do that would be to specify this angle theta between the x-axis and the x-prime axis. Okay? Now, here's the bit of mathematics that you may not have covered. Does someone know how to actually relate these coordinate variables? As in, can we write down something that actually looks kind of like this? I would want to be able to say this. I want to be able to say that x1 prime and y1 prime is equal to some kind of function in terms of x and y, and possibly this theta. Like you may have covered this, maybe not. I forget when I learned this, so I'm not sure if it's something you're supposed to have learned before Physics 4c. It's possible that you haven't learned this, yes?
It can be represented to multiply a matrix, represent.
Yeah, matrix multiplication, that's one way to do it. So once again, I'm not sure when you learned this. It might be Math 3F, or it might be before then. So, or is it 3E or 3F that's a linear algebra? 3. So it might be 3E, it might be something else. So let me actually write it down, and I will help you make a sense of, is this actually correct? So this x1 prime coordinate, it can be represented this way. X cosine theta, and I have to be careful here. This looks bigger, right? So I'm going to guess plus y sine theta. And this y1 prime coordinate can be represented as y cosine theta minus x sine theta. Pretty sure this is correct. Let's double check. I can double check this with some special points that are kind of easy to represent. So let me double check it with, I don't know, special point here. Oops, blue is the wrong color to use there. Special point, do I want to use red? Sorry. So once again, this is theta. So let's consider this point, which I will say is at the coordinate 1, 0. X is equal to 1, y is equal to 0. Good? Then when you look at this point, it's, so these are its x prime and y prime coordinates. This is the x prime coordinate of this point. Drop down something perpendicular on the axis. And this is its y prime coordinate. Yeah? So let's see for this one point if the expression I try to remember from memory is correct. So, well, I have a right triangle. This is actually a right triangle I can use. This is a right triangle, right? So the x, or 1, is the hypotenuse. And x prime is the adjacent side of the right triangle. So x prime is hypotenuse times cosine theta. And this is 0. Sounds right? Right? Okay. And the y prime coordinate is the opposite side. But it's below the axis, so it's negative. So y prime is, so this is 0 again, minus x sine theta. Good? So, all right, that works out. Let's just double check it with one more point, with a point that's up here, 0, 1. And I guess I won't belabor this point too much, but the thing about unit vectors is that if this formula I wrote down is correct for x hat unit vector and y hat unit vector, then it's going to be correct for any other vectors that I can write in terms of these unit vectors. So this coordinate is 0, 1. So let's see if it's correct. Let's drop down the drop down a point perpendicular to the axis here. So this is my x prime. Drop down point perpendicular to the axis. This is my y prime. And this angle here that I'm labeling, that's my theta. Right? So I'm looking at this right triangle here. This right triangle here. So y prime is the adjacent side. So y prime should be equal to 1 times cosine theta minus 0. And the x prime coordinate is the opposite side, but it's not positive, and it is positive as you would expect. Okay? So this is the, this is, well, not you could, this is the expression of the rotation transformation. Right? I'm kind of trying to model it here. This is Lorentz transformation. This is a rotation transformation. And what you're transforming your reference frame. Here, your reference frame is boosted at some speed. Here, your reference frame is rotated. Okay? And to wrap up this discussion of rotation transformation, that I guess from looking at your faces, I guess this is not covered in the math before Physics 4C. Or if it is, it's not very emphasized. When, do you remember covering this in any of your classes?
We covered rotation matrices and linear algebra, but
That's Math 3, yeah.
I don't think I saw that.
So before Math 3, you haven't seen this. All right, so this, that's why, so we are going to make Math 3 co-requisite to this class soon, and that's one of the reasons. All right, so I can actually represent this with the matrix multiplication. How many here know how to multiply two matrices together? Okay, enough of you, but I see enough of no hands, and one or two maybe. So let me just write down the matrix multiplication rule. So if you have two matrices, let's say A and B, and if they are represented, I'll just do it 2 by 2 matrices to illustrate the rules. A11, A row first. So 1, 2, A2, 1, A2, 2, being multiplied with the B matrix, B11, B12, B21, B22. I think a matrix multiplication is covered in college algebra, right? Yes? Pre-calculus. Okay. So when you multiply, so this is the rule. I like to do it visually. You take the first matrix, you take the element along the row, and you are multiplying with element along a column of the second matrix. So this goes with that, this goes with that. And you multiply them, and then you have two multiplied terms, add them together. That sum becomes whatever row this was, and whatever column this was, goes into that row and column of the resulting matrix. So if I'm writing that down, this is what it would look like. It would look like, so A11 times B11 plus A12 times B21. And let me just do it for, I'll just finish out the whole matrix. It's not that long. So this still row 1, but then if I do column 2, it'll be A11, B12 plus A12, B22. And here it'll be the second row now, and then the columns again. So A21, B11 plus A22, B21. And then the last entry here is the second row multiplied with the second column. So A21, B12 plus A22, B22. And when you do this correctly, here are some features that, with the way I'm labeling the indexes, these are the features that you ought to expect to see. These indexes are always the same, 1 and 1, 2 and 2. So the things that are multiplied together has the same, same column index, the same row index. If it doesn't turn out that way, you did something wrong. And these remaining indexes here, the 1 here and 1 here, or 1 here and 1 here, that represents the index of where this element lives. It's supposed to work out that way. Good? So with this matrix multiplication in mind, this is how you can represent this transformation in a much more compact format. You can represent this transformation this way. You turn this into a column vector. So x prime and y prime. And you turn the right-hand side into a product of a square matrix, which is the rotation matrix, with another column vector. So the right-hand side is where you have your transformation operation you're going to do. That's going to multiply to a column vector. So a way to look at it is this. You have your coordinate axis. You do a transformation to it that turns it into new coordinate axis. And the transformation that you do looks this way. Cosine theta, let me do it carefully. Sine theta minus sine theta and cosine theta. Good? Yeah, this is a particularly clean way of writing down this transformation, because anything that's specific to that state, coordinate, or whatever, it's separated out into these two vectors. And the information about transformation, it's all contained in this square matrix. Okay. So this is an example of linear operation, which we'll, I guess, cover in Math 3, and then you take it.